Good morning, good afternoon, and good evening, everyone. Welcome to fourth session of Citizen Science Discussion Series. I am Rajaram from Smartphones for Water, and I am thrilled to be hosting this session today. We understand that participants are tuning from various time zones, and we truly appreciate your presence here today. We are still waiting for some more participants, but we are going to start the session. Citizen Science Discussion Series. It is organized by Smartphones for Water. It is a non-profit organization dedicated to leveraging citizen science, smartphone, and young researcher to tackle global water challenges. At Smartphones for Water, we believe that by connecting people and technology, we can democratize water data collection, foster local capacity, and make meaningful contribution to water resource monitoring and management worldwide. So the series is an initiative by Smartphones for Water, a platform designed to bring together water researchers and practitioners from around the world who are involved in different citizen science projects. It is all about collaboration, knowledge sharing, and creating a space where we can learn from each other's experience and innovations. So we believe that the collective expertise of the community holds an immense power to drive the meaningful change. It is my absolute pleasure today to introduce our esteemed speaker, Dr. Salvador Pena Haro. He holds a PhD in hydraulic and environmental engineering from Technical University of Valencia, Spain, and he did his postdoctoral research at ETH Zurich in Switzerland. With over 20 years of experience, Dr. Pena Haro has dedicated his career to advancing water monitoring, modeling, and management across diverse regions and contexts. Currently, he serves as Chief Technical Officer at Photrack AG, an innovative startup specializing in developing image-based monitoring technology for advanced water monitoring. Through his work, he continues to push the boundaries of innovation, particularly in making hydrological monitoring tools more accessible and impactful for communities worldwide. So our today's presentation will be followed by discussion. The presentation might last from 30 to 40 minutes, and then we will have discussion. And we will try to wrap it up before not maybe we can have 40 minutes of discussion followed by the presentation. And the session is being recorded for your information. And please turn your mic off during the presentation. Today, our guest speaker will share his insight on DischargeApp, an innovative smartphone-based tool that is revolutionizing water monitoring by enabling local involvement and citizen science. So we are very privileged to have him here. So without further delay, I would like to request Dr. Salvador Pena to start his presentation.
Right. Thank you very much. So I will share my screen. Yep, as it was mentioned, so my idea is to present the DischargeApp, which is a mobile application for flow monitoring in open channels. And also discuss a bit the ideas that we had behind when developing it, how we intended its use, and the challenges that we've been facing. So by water monitoring, as I said, I mean flow monitoring on open channels. My presentation is divided in mainly 4 parts. First is why we developed this mobile application. The second one, I will go briefly on what are the methods behind and how the mobile application looks like, how we intended the mobile application to be used, and challenges that we have faced, and some lessons that we've been learning along the way. So there is, I guess we all know the importance of water monitoring and to have data on water. But this also, I think we are all aware that there is a lack of data. And many of that lack is because of many reasons. But one of them is that because traditional methods to monitor water flow, they are normally expensive and difficult, like to buy, to maintain, to install. But also they are many times difficult to use. So the idea of the DischargeApp is to try to overcome these challenges by creating a very cheap, actually the mobile application is for free, solution to monitor the flow, and also very easy to use. So the Discharge app is, we think that, so as it says, it's an application, it's a mobile phone application, which can be downloaded from Google Play. It's in Google Play since 2016, even though the development started some years before that. So like 3 years before, we already had the first version that we were using. And as I will show during my presentation, it has several advantages. One of them is that, well, it's an application, it's relatively easy to use. It's non-contact, so it's very safe to use when there is high flow. There is no equipment left outside, no? So the only equipment is the smartphone. So there is nothing to be stolen. And yeah, so all the workflow is automated. There is all the data can be sent to backend, can be visualized. There is no need to be writing values or anything. So all data is automatically transferred if there is internet connection. If there is not, also the mobile application can be used. No? The only difference is that the data remains local in the smartphone. And the last one is it's an optical measure. So at the end, we see an image with some, for example, like the image that we see on the screen, with the velocity vectors that are used to calculate the discharge. We also see a line indicating the water level. So by this, we already can have an assessment if that measurement was done properly or not, if that value is more or less accurate, just by seeing that image. So that image at the end has a lot of value. So going a bit into the methods, what is inside of, or how we do the discharge calculation. For this, we use velocity area method. So we need 3 things. We need to know the cross-section of the river or the canal. We need to know the bulk velocity, and the water depth, no? To know the wetted area. And on the mobile application, the way that we get the depth average velocity is by measuring the surface velocity and by transforming that surface velocity into an average, depth average velocity. Then knowing the cross-section and knowing the water level that we also measure with the mobile application, we can get the discharge. So first, the first variable that we measure is the surface velocity. And as it can be seen in these 2 slides, these are taken from a video that was taken at 30 frames per second, and this is 1 frame and the next frame. And of course, visually we can see that there is movement on the surface of the water. And the idea is to measure that velocity of the surface of the water with some algorithms. So we do some image analysis where we identify that displacement on the surface of the water. The first step is to divide this image. So we record the video, we separate the frames, then we subdivide that image in small regions like this one. And the image on top is 1 frame, and the image below is the next frame from the same region. So actually we can see that there is a displacement of some structures on the surface. So what we do is then we just do a cross-correlation technique, or there are a couple of techniques implemented on the mobile application. But let's say then what one of them is the image velocimetry. So with that, we measure that displacement. And then for each one of those regions of the image, we can get a velocity vector as it is shown in this final image. But what we do, the first step is that we get those velocity displacement on pixels and the pixel scales. So from the image, the only thing that we know is pixels. So we have to transform those pixels to meters per second. And for those, we do some camera calibration. So the end result, as we can see here, is that we can see the velocity in meters per second, as well as the discharge. And all those steps are done inside the app. So the user does not have to interfere with that process. The user only has to record the video, select some ground control points, which are used to do the transformation between pixels and meters, define the water level, and then everything at the end is done automatically. So once that we obtain the surface velocity, and because one of the input data that we need is the cross-section, the mobile application automatically calculates that depth average velocity. And then we take that for different transects on the cross-section, then it's integrated, and finally we get the discharge. While this probably sounds a bit too many steps, probably a bit cumbersome, all the calculations that they have to be performed, all of these are done automatically. So for this, what I want to show now is a video that shows the real usage of that of the mobile application. So the only thing that we need is an Android phone. Now, right now it's only available on Android, is to open the mobile application like any other app, choose the site where we want to measure. Then the application guides us to record the video. The video is a 5 seconds long video where we should keep the phone very stable. Once that video is recorded, the mobile application guides us to tell where on the image our ground control points are located, which we need 4 ground control points. They have to be always visible on the view. Then already here, the mobile phone is doing some calculations. And here I have to detect the interface between the water and the shore. And here we are getting already the water level. And as you can see, it's already a metric unit. So in this specific case, it's 80 centimeters, the water column, you know, on that river. So this is already the first measurement that we can do with the mobile application. The next step is that it asks us just if we can, to delete the measurement or keep and proceed to process the video. All the processing is done locally on the phone. There is no data transmission at this step. So after 20 seconds, the calculation is done. And the last thing is just to send the results to the backend. So we have a web application where it can collect all the data. Or as I mentioned before, it's not needed to push that data. That data can stay on the phone. So many places there is no internet connection, so there is no need to send the data. Or once that I'm in the office or I'm back in a place where I have internet access, I can push all that information to the cloud. So as we could see, the steps are very, very simple. It's really record video, click 4 clicks on the ground control points, give the water level, and do the processing. And that's it. And takes less than 1 minute to do the measurement without touching the water. That's I think that's very important. And the only hardware needed is a smartphone. But here I'm starting the explanation where already the ground control points exist, you know, when the site is prepared. And that's, so there are some preparations that we have to do at the site, but those are only done once. And if the cross-section on the site does not change, if the ground control points do not change, the measurements that I'm going to explain now have to be done only once. And what we need to introduce into the mobile application are the coordinates of 4 ground control points. Or we can introduce just the interdistances between those 4 ground control points. As we can see here, like, one way is to get really the coordinates X, Y, Z of each ground control point, or just measure those interdistances between the ground control points. And we can introduce that data directly into the smartphone. And in a small channel like this one, that exercise takes like 15 minutes to have it ready. And again, it has to be only done once. And after that, anyone that has access to that has the mobile application and has access to make measurements on that side, can make a measurement in less than 1 minute. Yes, and the other one is to introduce the cross-section. Also here, this cross-section is relatively simple. It's a trapezoidal canal. But also we can do any type of cross-section. Can have any geometry. The problem is that when it's not a regular canal, takes longer to make the measurements, the survey of the cross-section. And these are some steps how to introduce the data into the mobile phone if for a non-regular cross-section. As I was saying, also the mobile phone can be, the application can be used to measure only the water level. We do not have to go all the way and calculate the discharge. And also, there is another option to estimate the discharge. One is by processing the video, but the other one, if I also am able to introduce a rating curve, the relation between water height and discharge. And just by knowing that water height, and if I have introduced that rating curve, the estimated discharge, like shown in this screen, can be calculated based on the rating curve. And I can send this image and this information also to the backend and the web application. Or I can proceed and process the video and get the results. So that's mainly how the mobile application looks like and the main features. I just want to stress that now has been all updated. And for example, I can process any video. Like for example, in this case, was a video taken from a drone that then I downloaded into the phone, and I can process also with the DischargeApp. Or I can use this DischargeApp also to record events. It can be like a flooding on the street. I can record it, and then knowing some information afterwards, like that geometry, we can calculate the velocity and the discharge. Going backwards. But this application, I would say, is more than just the measurement. It's more than just a sensor, using that phone as a sensor, because that application is connected to a web application, and that web application allows us to do more things. For example, we can see the measurements done. I can see the date. I can see who made it. I can see the water level. I can see the velocity. I can see the discharge. I can see an image per measurement. I also, like seeing here, there's a proof image done per measurement. I can see the time series done. And also there is a validation process, since just by seeing an image, I can detect if the measurement there is a mistake done during the procedure. I can reject some measurement. So there is a validation process implemented on the web application. But also I can use the web application to see all the sites, even to add users, remove users, add permissions to different users. For example, some users can change the parameters of the site, like that cross-section, the coordinates of the ground control points. And some users can only have rights to take measurements or to visualize the measurements. So this creates, we can create the structure of people that they are, that they have the know-how on how to do the survey, for example, and to avoid that someone that does not have that know-how that accidentally change some parameters on the site. Also, I can use this web application to also modify the parameters on that site. So someone on the field can introduce that cross-section, for example. But if I see, or if I want to update it, I can also do it from the web application. And the next time a user opens the mobile application, we'll have all the updated values again, no? Without the need of doing anything. Just open every time the mobile application is open, goes to the backend and updates all the parameters. So the idea of having this mobile application was that, or the value that we see on this mobile application is that can be used by anyone that has I mean, I guess the only requirement is to have a smartphone, then to install it, register, and to use it. And in the title of my presentation is the word local involvement. And I want to make a distinction between citizen science, which I'm not, as I understand citizen science, and I have probably only my point of view, but how I make the distinction between citizen science and local involvement. So here I copy one definition of citizen science. I mean, there are many, right? But there are probably this covers more or less like what is understood by citizen science. And to me, I see a difference when I think on local involvement. Local involvement is not a research involved. It's not that the population wants to have more knowledge about discipline, or that they want to be involved on data collection for a purpose on a research. To me, local involvement is because there is a need to know, for example, in this case, how much water is used for irrigation, how the water is being allocated in an irrigation district, are illegal discharges to the environment. So there are many places or situations where this information is needed. As I was saying at the beginning, there is, and in many of situations, the traditional methods do not work in these circumstances. So local involvement is where we want to involve a community where they having these problems, and they want to, for example, in this specific case, have data that they can take better decisions. And one of the advantages of having this local involvement is also that at the same time that they are gathering the data, it creates awareness about the problems, creates ownership because that people went to the field and collected that data. Also, to do that data collection has to be a know-how transfer, has to be capacity building. So this strengthens the communities. So what we thought is that the DischargeApp can help on this by being a low-cost technology, will incentivize to go and do those measurements. The community being involved on those measurements will create awareness. They will have trust on that data because they were involved on that data collection. And then we'll have that data that will ideally have an impact on having better decisions. So that was our idea. Also, we thought, at some point, The Discharge app is there. You can download from Google Play. We have many tutorials. We have a manual, very easy to use. We need 7 clicks. Anyone can use it. But when applying it in different projects, we have learned several things. That first is we were kind of naive that they were going to use it just like that. And we realized that the mobile application was not being used as we thought it could be used. So inside of the framework of different projects, the mobile application was used, and we identified different key points that we have to follow to make these type of applications to be used. First was like to properly inform the community. Someone that probably knows how to set up a site, how to place those ground control points, how to introduce a cross-section. They have to be trained properly. Very important has to be a protocol, how to measure, when to measure, who has to go, the time of the day. There has to be assigned people to do the data collection. And then has to be someone that can support if there are questions, feedback. There has to be quality control on those measurements. So it has to be a very clearly defined workflow. And the most important thing that we learned is that probably it's the last 2 points in this slide. That people had to be paid, even though that data was asked by the community. For example, in irrigation, some people want to know how much water they are receiving, and they want to measure it. And while that data is for their own good, still we realized that if there was no one really allocated, or a person in charge of taking the measurements, no one really went to take those measurements. And that person have to be financially compensated to go and take those measurements. And then it's like, okay, we are collecting data, and how to make use of that data, how to make water management plans, how to better allocate that water. So we need an institution. We need a strong institution behind. That institution would be ideal if it is the government, but can be any institution that the community has trust on. But there is very important, those 2 points. And from our experience, I think after the projects are over, normally the measurements stop. There is no continuity on the measurements. And I think it's because of those 2 main points. There is a lack of money, even though it's small compared to other costs that some data monitoring can have, and because of the lack of some institutions. So with that, I just thank you for your attention.